Hola, chaps. Let's learn.
Hola, chaps. Mr. Turk here. This is primarily for my physics students. I have many little items about waves that I wanted to teach you and explain to you and demonstrate for you over the course of this unit. And now we're kind of scrunching up against the end of the unit on the calendar. So I will just randomly put out a whole bunch of stuff about you. First of all, I'm going to talk about sound. And sound is a mechanical wave. And one of the properties of a mechanical wave is that there has to be some substance there for the wave to go through. There's a famous movie poster from the 1970s or so, and the caption said, "In space, no one can hear you scream." And the point of that movie poster was you need to have air for sound to propagate from point A to point B. And in outer space, there is no air, there's no material whatsoever. And therefore, you can't hear sounds through the vacuum of space. The sun, we believe, is actually extremely noisy, but we can't hear it here on Earth because there's no air between the surface of the sun and the surface of the Earth to transmit the sound that the sun makes. So be aware that mechanical waves require a medium, some substance other than a vacuum for them to go through. When I'm talking, the sound of my voice travels through the air and you process it when you hear it. When someone inhales helium, it changes the speed of sound in their vocal cords, and therefore they sound like Donald Duck. They're talking at a higher pitch. That's a side effect of how the speed of sound changes at different materials. I've been explaining about polarization and demonstrating that with the polarizers and analyzers. Well, polarization works for transverse waves, but sound is a longitudinal wave. The direction of vibration of the air molecules is in the same direction as the wave energy itself is going. And under those conditions, if I were to try to put up a grating and have it affect the sound waves going through it, it wouldn't be able to trim out any part of the sound wave. So, a characteristic of a sound wave is that a sound wave cannot be polarized. Light waves, which are transverse waves, can be polarized. Sound waves, which are longitudinal waves, cannot be polarized. I want you to be aware of that. The speed of sound depends on the substance through which it is traveling. If there's a vacuum, it can't travel at all. In air, at 0 degrees Celsius, it travels at 334 meters per second, but that's at 0 degrees on the Celsius scale. It goes up from there. And in a good high school, they would give you the formula that has to go as the square root of something or other. But here at Cerritos, the way I teach it is add zero point 0.6 meters per second for every degree that it goes up on the Celsius scale. So at 20 degrees Celsius, which is about room temperature, that would be an increase of 12 degrees. 334 plus 12 means at room temperature, the speed of sound is 300 and, I see I put the wrong number down here in the first place. This should be 334 meters per second, should it? Let's look it up on the official thing, and this was supposed to be a 1. There we go. Sorry. So correct the number, 331 meters per second at 0 degrees. At 20 degrees Celsius, I'm going to add 12 more degrees to that. And so at room temperature, it would be 343 meters per second would be the speed of sound in air. All right, 343 meters per second at more or less room temperature, 20 degrees Celsius. And as far as our process goes, we have this physics reference sheet that you allegedly have a copy of, and it mentions that the speed of sound in air at 0 degrees Celsius is 331 meters per second. And I also have a formula on the sheet. There it is. The speed of sound in air is 331 meters per second plus 0.6 meters per second for every degree on the Celsius scale that you go up from there. All right, so that explains that formula on the reference sheet. There is an entire table that shows the speed of sound in various substances. Here it is in air, here it is in helium. So for someone who inhales helium from a balloon, now the speed of sound is so much faster that the frequency becomes shorter and the pitch sounds higher and they sound like Mickey Mouse or Donald Duck. Donald Duck, I suppose. In water, it's much faster, and seawater is slightly different from fresh water, even faster. In general, but not strictly always true, in general, the speed of sound is fastest in a solid, then less fast in a liquid, and then least fast or slowest in a gas. It's not strictly true. There are exceptions to that general rule. But as a general rule, speed of sound is fastest in a solid, slowest in a gas. All right, so there's the old Western movies where the cowboy puts his ear to the railroad track and he can hear the sound of the train coming miles away, and he can hear that sound propagating along the iron railroad track faster than through the air above the railroad track. All right, so I'm going to explain that. Then there's this issue of lightning. I was watching a TV show with my wife earlier this week in the evening, and sure enough, as is commonly done in a Hollywood production, there's the flash of lightning, and immediately at the same time, you hear the peal of thunder that goes with the lightning. And as usual, that's wrong with one exception. The exception is if the lightning is striking exactly right where you are. In that case, yes, the lightning and the thunder come at the same time. But as it turns out, the speed of light is about 1,000,000 times faster than the speed of sound in air. This is 343 meters per second. The speed of light is 300 million meters per second in air, in space for that matter, in a vacuum. 3.00 times 10 to the eighth meters per second. In fact, that's listed on this reference sheet, isn't it? Speed of sound in air, speed of light, I should say, in a vacuum, 3.0, that's 300 million meters per second. So in round numbers, the speed of light is 1,000,000 times faster than the speed of sound here on Earth. Now, a long time ago, Galileo got into an argument with someone about that. You could see a cannon flash and then hear the sound afterwards. And the common belief was the speed of light instantly showed up and the speed of sound took a while to get to you. And Galileo argued against that and said, no, we don't know that the speed of light is instant. We just know that it's way faster than the speed of sound. And I believe I've already explained to you during the regular school year the whole long story, which I just love, about how Galileo tried to measure the speed of light when he was a kid. He had his friend go on a hilltop 7 miles away from him outside of town at night, and he gave him the instructions, look, when I flash you, I want you to flash me back. And of course, he's talking about opening the shutter on a lantern at night. And this is the first known attempt to scientifically measure the speed of light. Galileo's conclusion was it was way faster than human response time, which was correct. When Galileo was in college, he went to the uh, Leaning Tower of Pisa, Padua University there, and observed the chandelier swinging back and forth. They had the candles on it, and from that realized that the shorter the rope, the faster it would swing back and forth. And he shared that information with Christian Huygens. Between the two of them, they invented the grandfather clock from all that. And Galileo was famous for being the first person to point a telescope up into the sky and report his observations. All of that led to the development of astronomy, optical astronomy, and the improvement of clocks over time. And shortly after Galileo's lifetime, clocks were so good, telescopes were so good that observers could see that the moons going around Jupiter would appear to show up 15 minutes earlier, up to 15 minutes later over the course of a year. And from that, an astronomer named Ole Romer was able to figure out the speed of light based on Copernicus's measurements of the size of our solar system and realizing that, oh, the reason the satellites appear to show up early or late as they come out of eclipse around Jupiter is because of the amount of time it takes light to travel across the distance of Earth's orbit around the sun. So, elegant story, folding all that together, something I derived from one of Isaac Asimov's articles, I believe. But back to this nasty business of Hollywood showing lightning and immediately you hear the sound of thunder that goes with it. We now know, that's incorrect. What it should be is that what you can do is when you see lightning flash someplace, you should start counting to yourself immediately. 1 Mississippi, 2 Mississippi, or whatever your timekeeping is to count off seconds. And determine, well, how many seconds did it take for you to hear the sound once you saw the sound? So, knowing that the speed of sound is 343 meters per second, and knowing that 1 mile is 1,609 meters, I believe that, yep, there it is. So that's a little reference here on this reference sheet. 1 mile is 1.609 kilometers, meaning 1,609 meters. You should be able to calculate right away how much time does it take for sound to travel a distance of 1 meter. Calculate, please, at 20 degrees Celsius. Okay, my answer is 4.69 seconds, which you can't quite read because I'm not going to, I suppose I can lower the contrast. 4.69 seconds. So round that off, call it 5 seconds. When you see a flash of lightning, for every 5 seconds that it takes for you to hear the thunder from it, that lightning strike is 1 mile further away from you. Okay, so if you see lightning and 25 seconds later you hear the thunder, you mental processing can figure out, oh, that means it was 5 miles away. But wait, you ask, what about the speed of light? Well, it's a million times faster. So if it took 5 seconds for the sound to get to you, it took 5 microseconds for the light to get to you. Way, way faster than human response time. So it's insignificant as far as making a difference on our calculations. It would only matter out in the fifth or sixth decimal place or more if we were to work it out, probably around the fifth decimal place. So don't worry about it. As soon as you see the lightning, start counting. And in this course, I used to have test problems based on that. It said, when I go outside and I watch the fireworks from Disneyland, which I used to be able to see from where I used to live, I counted how many seconds it took from when I saw a particular fireworks burst to when I heard the sound of that explosion. And from that, I determined the distance, the straight line distance from my home to Disneyland. And if you had gone to graduation this year, at the end of graduation, they always set off fireworks. If you were to watch the fireworks and then count how many seconds from when you see it to when you hear it, for every 5 seconds, that would correspond to 1 mile of distance. Still true today. All right, next, about interference, there is a PhET simulation. And I think what I'm going to do is edit this video and insert the PhET simulation into that. Talking about it first, it's got a simulation showing waves when you open a faucet and it goes drip, drip, drip onto calm water. And let's say that every dark spot is the trough of a transverse wave, and every light spot is the crest of a transverse wave, and they're spreading out in all directions evenly as a function of time. So, what happens when you have two sources of water hitting the surface at the same time? The answer is each one is sending out circles getting larger and larger, centered on where they hit the water. And they can overlap with each other. Well, when a crest combines with a crest, that is called constructive interference. And where a crest combines with a trough, that is called destructive interference. They cancel out. So that leads to amazing but true statements about sound and light and all waves in general. Here it is. Sound can combine with sound to create silence. I kid you not. Light can combine with light to create darkness. And all that is because of constructive and destructive interference. So when they did the Voyager around the world flight back in the 1980s, the nonstop flight. There were these two pilots. One had the last name Yeager. I forget the other one. A man and a woman. They were in this little tiny cockpit. They had an engine in front, engine in back, and the fear was that they were going to lose their hearing during the 18 days that it took for them to fly around the entire world nonstop without refueling. And just newly invented back then were noise canceling headphones. So the way it works is you put the headphones on your ear, and on the outside of the headphone is a little microphone listening to all the sound coming in from outside. And on the inside is a little speaker, and the wires are crossed so that the polarity is reversed onto sound waves. Remember, sound is a longitudinal wave. So it's really a compression and a rarefaction. Compression where the air is squeezed together, rarefaction where the density of the air is less than ambient. And so coming out of the speaker would be a rarefaction coinciding with the compression from the real sound coming in from outside. So the compression coming in from outside combining with the rarefaction coming from the little speaker inside the headphone would cancel each other out and it would become quiet. So that's how active noise canceling headphones work. And the two pilots wore it somewhere around day 16 or so. The units failed or the batteries died, but that was so far through the entire 18-day journey that no, they didn't lose their hearing. They were able to go through the last 2 days listening to the sounds of the engines as they completed their round the world flight. In fact, I have on display an image in my office of the aircraft as they were coming in for their landing. I took my parents up to watch that at Edwards Air Force Base. This is the PET sim about wave interference. When I turn on this water faucet, it drips, drips, drips at a steady rate. And what you see coming out from it is the wave crest and trough spreading out. Let's say that where it's white, it's a wave crest, and where it's dark is a wave trough. Okay. Now I'm setting up the same PET sim with two faucets, and I'm turning them both on. They're each dripping at the same rate, and where the crest combined with a crest, you get a white area. Where a crest combines with a trough, they cancel, and you end up with this pattern being created. And based on the angle and the separation, there's a physics formula that goes with this that we don't care about this year. This shows that where you stand will make a difference between whether you are experiencing constructive interference or destructive interference at your location. What else? Light can combine with light to create darkness. So that's just a property. It has to be the same wavelength. I can't combine red white with green light. I can combine red light with red light, and it has to be phased just right. And this can be done. A guy whose last name was Young carried out experiments like this, and the Young double slit experiment is the name of it. If you want to Google it and look it up, the PET sim shows that when you have two sources emitting wavelengths next to each other like water drops in a pond, that there's a pattern that emerges where there's constructive interference here and destructive interference there. In fact, one year at Cerritos High School, we used the ASB speakers, set them up in the quad, separated by some, I don't know, 10 meters or so, and played one particular note coming out of each of the two speakers. And then we asked our students to walk around the quad, and anywhere where the sound was loud, put a little piece of tape on the ground. And anywhere where it was quiet, just move on. And sure enough, the students, and then at the end, we asked them to stand wherever they had put pieces of tape. And the result was you could see very clearly the interference pattern across the quad of where the sound had constructive interference and it was loud. It was just something fun to do. Doing it with light, you can duplicate Young's experiment with a couple of cards and a pinhole and a double pinhole. I'll leave it to the interested reader to look up how to do it on your own. Next, I want to at least address the concept of beat frequency. So beat frequency is a little bit different from constructive and destructive interference. Constructive, destructive interference, I was referring to the same wavelength, and to cancel it completely, ideally would have the same amplitude as well. So beat frequency is where we're generally talking about two different frequencies, two different wavelengths. And if I can't sketch this very well, but if I did, in fact, maybe I'll just go online and find a graphic to insert here. So I have a wave, and I have another wave at a different frequency. So what will happen is occasionally they're going to coincide with each other. And where they coincide, that's going to be constructive interference now for waves at two different frequencies. So they will sound louder. And later on, they're going to exactly be out of phase 180 degrees, which means the peak of one will coincide with the trough of another. Or in the case of sound, a compression will correspond to a rarefaction of the other wave. And so the sound would cancel, or the light would cancel. Same effect. The two waves would cancel out. And what you would hear if this was audible with sound waves is where there's constructive interference, it would sound loud. Where there's destructive interference, it would sound quiet. So here's an example of beat frequencies. I've got a blue sine curve and a red sine curve, and they're slightly different frequencies. Where they line up, you get constructive interference and a peak, and where they destructively interfere, you get a minimum. And so the bottom shows the summation of the red and blue waves, and you can see that there are two beats showing up in this diagram. And this is the whole trick used by the orchestra when they first tune up before they perform. The lead clarinet or whoever it is plays concert A, and that has something like 440 cycles per second of sound. And then the next clarinet sitting by that person plays on their clarinet, and what they're listening for is the sound of beats between the two instruments. Now, the lead clarinet is the person who tunes the entire orchestra. Everyone has to compare theirs to that person, to that first person. And each player is listening for the beats between their instrument and the lead clarinet player. If they're if they're hearing beats, then they're not in tune with that person. And the more frequently they hear the beats, the more frequently per second the waves coincide. So beat frequency is directly corresponding to the difference in frequency. So if the concert pianist is tuning her instrument at 440 hertz, and your clarinet happens to be at 443 hertz, then 3 times per second you'd have constructive interference, 3 times per second you'd have destructive interference. So you'd have a beat frequency 3 times per second. You go wow, 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 louder, softer, louder, softer, louder, softer, 3 times per second. You can't tell directly if your pitch is too high or too low, because if you had a frequency of 437 hertz, you would also have a beat frequency of 3 hertz. So it doesn't tell you if you're high or low, it just tells you how different you are from the lead clarinet player. And you adjust your instrument. So if the clarinet is too far one way, you can lengthen it. Too far the other way, you can shorten it. With stringed instruments, you can tighten them or loosen them to change the speed of sound in the material, which changes the pitch of them. Particularly on a guitar, stringed instrument, as they tighten it, you can hear the pitch change quite a bit. So that's how beat frequencies are used in the everyday world. Why you hear the orchestra all tuning to that first player before they perform, so that everyone is tuned to the same thing. All right, next on my notes here, I wanted to talk about natural frequency. Everything has a natural frequency of vibration. So I don't have a handy example to show you. Oh, actually, I have a non-handy example to show you. So the camera's not really doing anything useful right now. I suppose it's distracting, and I should probably just turn it towards the ceiling or something. Okay, so it's not interfering with this view. So what I want to focus your attention on is I have your tuning fork. And this tuning fork's got a little label on it that you can't read. It says 256 and the letter C on it. 256 means it's designed to vibrate back and forth 256 times per second. Now, for you humans, that corresponds to middle C on a keyboard, let's say. And it's mounted on top of a box which is hollow on one end and closed on the opposite end. So this box is really designed to be optimal at a particular temperature on a particular planet surface. It's designed for use on Earth around room temperature, where the solid end is going to act like a reflector for the sound waves. And that means, I believe, it has to be an antinode. And then the open end acts like a node, if I remember that correctly. It's one way or the other. And actually, I don't care this year. In other years, yes, we used to teach that stuff. When you make this thing vibrate, by the way, you should not be using metal on metal, because that will slightly deform it and slightly change its properties. So I have my Brazilian nutcracker here, gift from the Barbosa family. What I'm going to do is just whack it. And depending on the quality of the audio system here, you should hear this tuning fork vibrating away. 256 hertz, the two tines, as these are called, go apart, come together, go apart, come together, 256 times per second, compression, rarefaction, and it goes to the air and you hear it. In the old days, I used to have a second tuning fork and I could put these next to each other and create beat frequencies by slightly adjusting the mass attached to one of these, like with a paperclip. But for now, I just want to point out everything has a natural frequency of vibration. This one is designed to vibrate 256 times per second. When the space shuttle used to land at Edwards Air Force Base, it would send out a double sonic boom while it was descending to a landing. And it turns out the natural frequency from one sonic boom to the second one matched the natural frequency of the skyscrapers in downtown Los Angeles, which means the first boom would push the building off to the side, and then the building would sway back, and then the second boom would arrive just in time to push it a second time. It's as if you were trying to give your sibling a ride on a swing set. You time your swings so that every time they're back ready to be pushed, that's when you give them a push. Well, that's what happened when the space shuttle was landing. The buildings would sway and then sway even more seconds later when that second boom hit. The timing from one boom to the second is not terribly long, but again, that's a detail we don't care about today. What I do care about is that all solid objects do have a natural frequency of vibration. Even this planet has a natural frequency of vibration. I believe it takes 88 minutes for a wave to travel through this planet from one end of it to the opposite side of it. But what you can do for educational purposes at home is find a glass in your kitchen. In this case, I chose to use a wine glass, but essentially any decent glass can do this job. I've put a little bit of water in it, and what you can do is take your finger and wet it in the water, set this thing on a surface, and rub your finger. And what you're doing is you're making this glass vibrate at its natural frequency. This is called resonance. What's going on is the spacing of your fingerprints stick and then break free, stick and break free, and it's vibrating the material of this, in this case, wine glass, at its natural frequency. So for fun, you can do that. And by the way, normally I have a container where I can dump the water out. I don't know if you can hear that. So the point is the bottom stem as well, wherever the microphone is. I forget where the microphone is. So I'm having fun. You should have fun in the name of physics. Volunteer to wash dishes tonight and take a moment while you're washing the dishes to create this resonance here, this natural frequency. So what I plan to do is on this tape, edit it and insert into it right about here the video clip that was shot in 1940, shortly after the invention of the color movie camera, of the Tacoma Narrows Bridge. As an engineer and a physicist, the Tacoma Narrows is an exciting story. So I'll tell you the story right now, and maybe I'll narrate the video later as well. So, you guys are at the beginning of what might be the greatest economic contraction of the U.S. economy in your lifetime. It's it's currently equal the current quarterly report to the Great Recession of 2008, which you probably don't remember. And now it's approaching the magnitude scale of the Great Depression of the 1920s. So you took AP US history, you studied US history in the 1920s. Let me remind you, 1930s as well. There was the Gilded Era in United States history where we had sort of a Baroque engineering style. Take a look at the Chrysler building designed and built in New York City from that era, and you see it's a Gilded Age. Here's an image of the Chrysler building in New York City, the top of it. When the Great Depression struck in the United States, millions of people became unemployed. There were long food lines. Kind of sounds like today, I know. Well, it had a psychological effect on architecture as well. So instead of all this Baroque gilded embellishments to buildings and architecture in general, suddenly that seemed very wasteful and shameful. And therefore, the new architectural style was that simplicity is what's elegant. So bridges were being designed during the Great Depression. The Golden Gate Bridge in San Francisco should come to mind as an image of these suspension bridges that were being designed. And the philosophy being employed during the Great Depression was minimal material to do this. So the famous example is called the Tacoma Narrows Bridge, and that's up in the northern western part of the United States. There's this strait, and they finally decided to build a bridge, a suspension bridge going across it. And the philosophy was make it just a simple ribbon, elegantly arching over the water, minimal design. And they designed it to be about 400 times longer than its width. And it was a two-lane bridge And I think I will insert the video at this point and just narrate the events that followed from there. All right, Mr. Trick here, I'm going to narrate this. This is a YouTube video, and it was not too long after the invention of the color movie camera. So here is video shot of the Tacoma Narrows Bridge. It had been designed during the Great Depression as an elegant two-ribbon road arching across the strait. And as you can see, it's on a moderately windy day, and the steel and concrete bridge is twisting from side to side. Now, it had been twisting in the wind ever since it was opened on July 4th, 1940. And the newspaper reporter heard that this was an exciting story, so he hopped in his car with his faithful dog and drove to cover the story. Well, he was driving across the bridge when he realized he became the story. So he abandoned his car, and it's the newspaper reporter's car out there in the middle of the bridge. Now, this swaying that you see here went on for, I think, an hour and a half or so. And so at one point, Professor Farharkar, I think his name is, walked out in the middle of the roadway there trying to go rescue the dog. And when he got to the car, the dog just refused to abandon his owner's car. The dog was desperately trying to start the engine and drive the car to safety for his master. So the car, frightened as he was perhaps, stayed inside the car, and the professor was unable to rescue him. And you can see this is the steel cabling swaying back and forth. It's not during a hurricane. It was just kind of a steady wind, moderate winds that day. And yet the roadway is going up and down, I forget by how much, 9 feet or so on each side. And there it is. Professor Farharkar's son risked his life for the dog in the car. And sometimes when students look at the professor walking back from the car, they they jokingly say, "Hey, is that Mr. Turek in there?" But no, it's not me. And it's difficult to walk under these conditions. So he's kind of staggering. This video isn't the high quality as much as the original is, but you can see the figure of a human making his way towards you down the center line of this road. This is one of four bridges that were designed during the Great Depression, and as there he is, and no, that's not me. Seriously, no, wasn't me. The car is abandoned with the dog inside, and this couldn't be kept up for long. Now it swayed from July to November. This is November when this is being filmed, and families used to treat this as a free roller coaster ride to go driving across this bridge on a Sunday afternoon. It hadn't been this bad before, but this time it was this severe. That professor was apparently a university mechanical engineering professor, and he said, "Oh, this thing will be fine." Well, as you can see by this headline from this newsreel, it ended up, doggone it, collapsing. And even after the bridge tore itself apart, it continued to sway. You would think that at this moment, once the bridge had relieved itself of all the torsional forces exerted on it, that it would just settle down. But it actually continued to sway the two fragments of the bridge there. And over the next, I believe, 15, 20 minutes or so, even some more of the bridge continued to disintegrate. So this is after the main section had already failed, and you can see it's still twisting side to side. It became an engineering challenge. There goes more of it. To explain, why did this bridge fall down? The first thing engineers did was change the rules for designing bridges in the United States. If you bother digging up an image of the George Washington Bridge across the Hudson River in New York City, you'll see that the very next bridge that was designed after this disaster was discovered looks basically like a fort. It is double layered, it's got side reinforcements, it's a short, boxy bridge. This bridge, the Tacoma Narrows, was 400 times longer than it was wide. And now the engineering rules in the United States say You can't have a bridge that is more than 200 times longer than it is wide, designed and built in the United States. There were three other bridges of this type built during the Great Depression. They had issues. If I understand it correctly, as of a decade ago, that's probably the reporter there. As of a decade ago, two of the bridges were still in service on the east coast of the United States after they had been successfully reinforced to damp out this torsional condition. Many engineering studies try to understand why this bridge collapsed, and it's not an obvious answer. Why did it twist itself to pieces? Interesting, though, yes? Okay, I got to enjoy the video when I was a science student. Yes, I was a science student after the bridge fell down. Thank you. Okay, next I'm going to move on and say I need to explain a lot about resonance. Woo, yeah. Okay. Whoa, not that. Not the pig illusion. Where are we looking? Here we go. So, in my notes of what to share with you, the Tacoma Narrows is an example of resonance that's pretty exciting. But wait, there's more. Actually, there's only two things left on my notes. So now I'm going to try in real time to explain about resonance. Along with the interesting episode with the Tacoma Narrows Bridge, we can talk about your human hearing. So perhaps I'll dig up an image to insert of what a cochlea looks like. Inside your ear, you have this thing that looks sort of like a seashell. And once upon a time, you were only this big. And when you were this big, that little seashell thing, if you were to unwrap it, it would be kind of like a harp. So imagine that this is the top of the harp and there's the bottom of the harp. And this is when your little tiny fetus developing. So individual cells were strung from top to bottom of this thing. Now, the actual physical shape of the cochlea is that it's wrapped up and it looks sort of like a seashell. But if you unwrap it, then it looks sort of like a harp or piano set of strings. And each one of these has its own natural frequency. The shorter one would have a higher natural frequency vibrating back and forth, the longer one, a lower natural frequency. And so what happens? When you hear the sound of my voice, the sound waves are vibrating these things at their various natural frequencies. So when I talk, I have a certain pattern that I activate. And when you talk, it's a different pattern that's activated. And so your friends can hear the difference between the sounds of our voices. My voice sounds like an old white guy. Your voice sounds like a young student. And you can, tell them apart. Recognize your mom's voice. Recognize your best friend's voice. That's because they're emitting a different pattern, uh, collection of frequencies. And your brain turns every sense into electrical signals that are processed in your brain. So, what happens when you choose to use earbuds all day long to do your online learning at home? Or you have the speaker cranked up because you don't care about the other people that you're safer at home with, and you're just torching them with all the sound. Well, just like the resonance of the wine glass, if you have enough energy in the wave coming in, this thing is going to set up a standing wave. I can draw it. There it is, where there's half a wavelength from top to bottom. That tugging on the top and bottom is what is converted into an electrical signal and goes off to your brain for processing the various sequences, the various patterns that come out are interpreted not only as the sound of who is talking, but of course, there's further processing that says, oh, here's what that person is saying. Oh, I'm going to ignore him. Okay, well, if too much energy comes in on these strands of cells that are strung from top to bottom, the problem is they were strung when you're only this big, and now you're this big, right? So they're nice and tight and very large. And if too much energy comes in, then they can break. And when they break, it sets off an alarm, an electrical signal. I guess you could call it pain, but a signal that goes off to your brain that says, and you hear that as ringing in your ears. Yeah, that means if you've ever heard ringing in your ears, you've been damaging your hearing. The problem is we don't have the technology to restring these cells from top to bottom. And you might wonder, well, why does the ringing go away? And the answer is it doesn't actually ever go away. What happens is your brain reprograms itself to ignore it for the rest of your life. So the cells continue to emit their pain, as near as I can tell, and the brain just shuts that alarm off and says, okay, I know about it. And the way your hearing tends to become restored is through the upper frequencies that tend to match. So if this one wiped out, and if this one is at twice that frequency, then it will have a little bit of vibration that is harmonious. So it's a harmonic with the one that was wiped out. And your brain reprograms itself and says, oh, if this one is vibrating a little bit and the one next to it is still working and the one next to that is still working, then it sort of fills in the blanks and imagines that the broken one would have been transmitting that information. And then your brain goes on and processes it and says, oh, okay, so that's how your hearing appears to become restored, even though that particular cell there is permanently damaged and destroyed. So the point I wanted to share with you is don't overdo it as far as your hearing goes. The studies that I've seen show that 25-year-olds can't hear the sound of rain falling. Not that it happens often here in California, but if you were to go for a walk out in the woods on a rainy day and you have all the beautiful sounds of nature, the raindrops falling on the leaves, 25-year-olds can't hear that as well as 75-year-olds because we old people didn't waste our lives ruining our hearings with earbuds permanently attached. We had other issues. And so preserve your hearing. Don't overdo it. Don't put those earbuds in and crank them to loud for multiple hours per day. Particularly, do you really want to ruin your hearing playing a video game? That is the worst choice you could make, right? You should ruin your hearing listening to my excellent YouTube videos. Okay, so that is what I wanted to explain about resonance, natural frequency, and hearing loss. There was a question that came up on Wednesday during our Google Meet about the Doppler equation. And I thought, well, okay, I probably should mention that one. So for the Doppler equation, this is on the reference sheet. If I go find where my finger is pointing, there it is. Well, the Doppler equation, physics, there's always equations with all this stuff. So this says the frequency of the detector is equal to the frequency of the source times the speed of the wave in the ambient medium minus the speed of the moving detector, all of that divided by the speed of the wave in the ambient medium minus the speed of the source. Yeah, go do physics problems based on that. Or if you like, I'll make up an example right now. Let's say that I have a car and the car has its horn blaring and the frequency at which the car is blaring its horn is middle C, 256 hertz. Okay, and this car horn is going towards you and you're standing over here and the car is going at 25 meters per second towards you. So that's this velocity of the source moving towards you at 25 meters per second. Let's do this on Earth on room temperature sort of day. So the temperature, let's call it 20 degrees Celsius, and therefore the speed of sound in air is 343 meters per second, right? All the way back to here, short-term memory. Okay, so if the speed of sound is 343 meters per second, and you are stationary, not moving, that means the velocity of the detector, that's you, your ear, is zero because you're just standing there. The velocity of the source is 25 meters per second towards you. The speed of sound in air is 343 meters per second. What would be the frequency that you detect with your ears? You should expect that the sound waves coming from this thing are bunched together. They're piled up in front of this car. And therefore, the, the shorter from crest to crest, the higher the frequency. So you want an answer, you expect an answer that is going to be greater than 256 hertz. If you do the calculation and you get a number less than 256 hertz, figure you did it wrong. Okay, so the formula, copy and paste, says the frequency of the detector is equal to the frequency of the source times the speed of the wave. By the way, I'm trying to be generic here. This doesn't apply merely to sound waves. This is used frequently, ha ha ha, talking about light. So light is Doppler shifted, sound is Doppler shifted, all waves can be Doppler shifted. On Wednesday during Google Meet, I gave a little bit of background and explained that Monsieur Doppler, I don't speak French, hired a trumpet player, put him on a railroad car, and carried out a series of experiments in the late 1880s and developed this formula. So here you go. V minus Vd, which is the velocity of u, the detector, divided by V minus Vs, the velocity of the source. And this is numerator, that is denominator. And now let's plug in the actual values. So we have 256 hertz times 343 meters per second minus the speed of you standing there, which is zero, divided by 343 meters per second minus, and here's where I have to do a little mental check. I know that if the source is coming towards me, that the answer should be greater than the original value. And this is in the denominator. If the denominator becomes larger, then the frequency is going to be smaller. If the denominator becomes smaller, then as you divide by a smaller number, the result is going to become greater. And that's what I want and expect. So I'm expecting to make the denominator a smaller number. And that means as the car comes towards me, I subtract the 25 meters per second. If the car were moving away from me, then I would add the speed of the car. So there's a plus or minus sign here that's implied. If the car is coming towards you, subtract its speed. If the car is moving away from you, add its speed. And what about you moving? So if you are moving towards the car at 25 meters per second, then this numerator should become larger in value. And so you would be adding your speed towards the car. And if you are running away from the car, maybe trying to save your life, then you should subtract your speed from the speed of sound in air in this case. So be aware that there's really a plus or minus sign, and it's based on the direction that the source is moving. It's based on the direction that the detector is moving. Your ear is the detector for this problem. And so just to finish it off, into your calculator, you probably already did this, 256 times 343 divided by, and no, I'm not going to do this in my head, 343 minus 25 in parentheses, and it says you can't read it. It says I end up with 200, I was trying to make that so you could actually read it. 276 hertz. I guess it's as faint as I can get it. Well, you can make that out. 276 hertz. And that matches my expectation. So as the car is coming towards you, you will hear it higher in pitch. After it has passed by you, if it doesn't kill you, you would actually hear it lower in pitch. And mathematically speaking, it would not be precisely the same difference in frequency. So you wouldn't say, oh, it's going to be exactly 20 hertz different. No, you have to plug it into the formula. All right. There's much more I want to cover. And today I'm going to try to get these things out to you. But at the very least, this particular section, I've talked about sound waves in particular, and then waves in general for some of the stuff. So sound waves in particular are mechanical waves. They need a medium. They're longitudinal. They can't be polarized. They have different speeds and different substances. In general, the fastest speed is in a solid. The slowest speed is in a gas. When you see lightning, rule of thumb, every 5 seconds that you count to yourself between when you see the flash and you hear the sound of it is how many miles away it is. 1 mile for every 5 seconds. And of course, that applies to anything that you see and then hear. So you see fireworks, start counting to when you hear it, 5 seconds per mile for the sound to travel to you. There's constructive interference, destructive interference. That leads to the possibility that light can combine with light to create darkness, that sound can combine with sound to create silence. Very interesting. Also applies to earthquakes. Certain earthquakes have had resonance effects based on the material that they're going through. Where I live, it's kind of more dangerous in other places for some parts of the soil. There's an interesting nature episode about a group of dinosaurs that were hanging out by a lake when an earthquake struck, and it turned the the shoreline into basically quicksand. And well, most of them ended up trapped in the sand and dying in place. So that's one of the side effects of interference that takes place. And of course, famously, uh, the woman singing wine glasses, shattering it with the sound of her voice. There's a scene in one of the Harry Potter movies where the woman in the painting was trying to do that, and she had to cheat and smash the wine glass on something. There are YouTube videos that can show wine glasses shattering under the effect of just sound waves. Beat frequency deals with combining two different frequencies to create loudness and softness. All solid objects have a natural frequency of vibration. Resonance is making it vibrate at its natural frequency. And you need to be careful that you're not making your hearing those little cells that are strung there vibrating with too much energy. You don't want to break them. Once they're broken, your hearing loss is permanent. Hearing aids are a technology solution that's not the same thing as having your original natural hearing. And finally, dealing with that CK12 problem that's had you calculate a Doppler shift. Of course, I just applied it to sound in air, but the Doppler equation applies to all waves. So we use it as one of our ways of describing that the universe, we believe, is expanding because when we look at light coming from far away, it is shifted in frequency and wavelength to lower frequencies, which corresponds to a longer wavelength. And that means it's shifted towards the red end of the rainbow. And we call that a redshift. If something was moving towards us, then out of the colors of the rainbow, from red to violet, we would say, oh, it's shifting towards the blue end of the rainbow. And that's blue shifted. So stuff coming towards us, blue shifted, stuff going away from us, that's red shifted. And based on observations of distant galaxies, we believe that the universe is expanding because galaxies that are farther and farther away from us are greater and greater shifted to the red end of the rainbow. In fact, they can be shifted so much they're not even visible light anymore. They're now infrared light. 3C273 quasar comes to mind. You can look it up. That's enough for now. All right. Ciao.